Okay, so I want to carry on talking about topology now. So in the last section we saw one example of a topological space, the circle S1, which we realised as just a set of points. It doesn't have to be a round circle, it could be any kind of wiggly circle. And we characterised this circle using a number which we called theta, which simply labels every point on the circle. So theta is a number in the interval 0 to 2 pi. And remember, we had to identify the 0 point and the 2 pi point as being the same point, which we visualize like this. So that's the interval 0 to 2 pi. And the endpoints we have to identify as the same point. Okay, so that's a fairly simple one-dimensional topological space. We can use this idea to construct some more interesting topological spaces. But before we do that, I just need to say a few things about the Cartesian product. So I defined the Cartesian product in the preliminaries video, so I'll just remind you. If we have two sets, A and B, we can form their Cartesian product using this cross notation, which is simply the set of what we call ordered pairs. And I'm going to call the little elements lowercase a and b, lowercase a coming from A, lowercase b coming from B. So now, this is an ordered pair. The first slot has to come from the A set, and the second slot comes from the B set. We've seen this already. But now I just want to give you a nice way to kind of visualize this Cartesian product. So if we consider our two sets now to be intervals, they don't have to be intervals, but it's easier to visualize for now. So I'm going to call the first interval A to C, and the second interval can be B to D. And now how might we go about forming the Cartesian product of these two intervals? Well, first of all, I'll just draw one of the intervals for you. So this is going to be A and C. Now, to form the Cartesian product, we need to produce the set of all the possible pairs with one element coming from the set A and one from the set B. So if we just consider now what one of these pairs might look like, let's choose an element in A, which I'll call A1 for now. Now we need to form all the possible pairs of this A1 element with every element in B. So essentially we can just plug in the whole set B. And what does this look like now? Well, we are essentially attaching an entire copy of B to the element A. So this might feel a little bit strange, but what I've drawn here, this line essentially represents all the possible pairs of the element A1 from A with every element in B. So now, this was just for a single element in A. So this was just for a single element in A, A1. We now need to do this for all of the elements in A. So we attach an entire copy of B to every element in A, and what we get is this kind of square or rectangle shape. So this is a copy of B, so it's going to go from B to D. And now any point inside this rectangle is just going to represent one of the possible pairings of the two elements of A and B. So this is going to be some AI and some BI. So another useful bit of intuition to think about this, if we think about Cartesian coordinates now, or the Cartesian plane, we know that this is the set R2, which is just the Cartesian product of two real lines. We know that we can draw this like that, and then any element in this R2 is just going to be a pair of real numbers, one coming from first R and one from the second R. So this is exactly the same object that we've constructed here, this Cartesian product. We're kind of representing it as a space, and all the points in this space are the corresponding pairs of elements, one coming from each set. Here we've just used closed intervals, so we have just a kind of finite square or bit of plane. Here we're using the entire real line, so we get the entire plane. Okay, so that was the Cartesian product in a bit more detail. Now we want to see how we can use this idea to construct a torus. So the torus, which is called T2, is simply the Cartesian product of two circles. So if we just remember what the torus looks like, it's this donut-shaped object. And now if I just draw on this figure these two circles, we're going to have one circle which will be the cross-section of the torus, and then a second circle which kind of runs around the long part of the torus. So if I just draw these again now separately, we have one circle like that, and then the second circle, and now you have to kind of imagine that this purple circle is lying in some plane, and then this orange circle is in an orthogonal plane. So this, from the side, it will look something like this, with the orange circle like that. And now, thinking about this as a Cartesian product, we said to form a Cartesian product, what we have to do is we have to take one set and then attach to it copies of another set. So we essentially are attaching this orange circle to every point on this purple circle. And now if you imagine, I could just kind of sweep this circle all the way around. I'm going to sweep out this toroidal cross-section here. Okay, so let's see how we can construct this now. So if we just remember what a circle is, it's simply a line segment with the endpoints identified. Okay, so this is going to be one circle. I'll call it S1. And now to form its Cartesian product with another circle, we just need to, at every point, attach another circle. So, as we've seen before, this is going to fill out a square like this. But now we need to remember that every point we're attaching is circle, so the circle that we're attaching, we need to make sure to identify its points with the corresponding edge points. So we'll see that we have to say, if I look at the circle attached at this point in the first circle, we have to identify this edge, or the point at this end, with this end. And similarly, if I do that for all the circles I'm attaching along here, what we end up with is that this whole edge becomes identified with this edge. And then likewise, because we could equally have just done this the other way around, attached a circle to every point on this one circle here, all of these edge points have to be identified as well. Okay, so this is what we end up with then. The Cartesian product of these two circles is this square as we had before, but now the purple edge, all the points on this purple edge are the same point as this purple edge over here, and likewise with the orange edge. And now to make it clear or obvious that we have to identify a point here with its corresponding opposite point horizontally, we can label each edge with an arrow, which just kind of tells you if you're travelling along this edge here in this direction, you have to identify the points on the opposite edge with a line going in the same direction. So if I just draw now a little subset on one of these lines, this little orange, or this little green arrow rather, has to be replicated oppositely in the same direction. Or if you like, all of these kind of now fibres, thinking about it, have to be identified with their corresponding opposite point. We could have done this in another way. We could have identified a point with its corresponding kind of not horizontal, vertically opposite, but diagonally opposite point. That would form something completely different, the Mobius strip or the Klein bottle. We'll talk about that in another video. Okay, so now let's see how to construct the torus from this square representation, which is sometimes called its fundamental polygon. So these two figures are homeomorphic as topological spaces, which we can kind of explicitly see by constructing a way to deform one into the other. So that's what I'm going to do now. If we consider now this square as being made of our ideal stretchy rubber, we can, first of all, if we glue these two purple edges together by bringing them round like that, we'll form a cylinder. So I'll just draw that for you now. We've joined this edge to this edge, so it's just going to become this kind of single seam down there. And then to make this clear, this is a cylinder. I'll just draw in those edges like that. So we formed our cylinder now. We need to remember our orientations. Okay, to make my life easier, I'm going to want to have these pointing the other way. It doesn't make any difference, but just is a bit easier to visualize. So if we do this wraparound like that, these orientations are both now pointing like that. So now what we need to do is we need to join this orange edge to this orange edge, making sure we orient their points correctly. So intuitively what we need to do is just bring this around, stretch it all the way around and join it back like that. So before we do that, I just want to quickly show you another way to visualize this orientation. So if we remember the right hand rule, here we have a kind of anti-clockwise turning loop. So it's a screw that's going to give us an orientation pointing upwards. So if you have some anti-clockwise loop like that, its orientation points out just from the right hand rule. And then similarly, if it goes the other way, it points, well, I can't, yeah, that's going the same way. If it goes the other way, so then likewise, if this loop is turning the other way, so clockwise, this is going to point downwards like that. Okay, so our two loops now, we have them oriented both, so their vectors are pointing like that. Now, when we join them together, these two orientation vectors have to match up and be pointing in the same direction. So in order to do that, we need to essentially because this is like a solid surface, we can't just smush it together like that. We have to perform a full 2 pi rotation so that this blue vector remains pointing upwards. So if I just kind of draw that for you now, I'm just going to redraw this picture but on its side. So this is our cylinder. We have our 2 orientations. And now we want to bring one of these around so that it joins up and forms a torus. So that's going to look like this. Okay, so what we've done, if we now call this circle, so we have this one with its orientation like that. So all I've done here is taken this circle, dragged it all the way around, so it's now coming in to meet this circle. Yeah, so let's just do this in stages to see how things happen. We first need to drag this circle up to there. If it gets dragged up to here, so it was going like that to begin with, and then I turn that, so it's going to be pointing that way. And now if I bring this loop around again, it's going to be turning and facing in the right way. So now I can just happily bring these together and join corresponding points to their opposite point. So that might have been slightly difficult to see. I'll just do that again. So we started with this cylinder, this picture I just redrew on its side. Now I'm saying that this green circle here is the same as that green circle. And now what we do is we pull this circle through a full 2 pi rotation. So its orientation vector goes from being pointed in that direction through half pi up to here. It's pointing in this wrong direction, and then all the way again through 2 pi. We arrive back at here and it's pointing in the right direction. So we need to always respect the orientation of our edges when we glue them together. So if we do this, we perform this full 2 pi twist of this loop, we glue them together and we form the torus. So all of that kind of more difficult to visualize stuff is simply just from this fundamental polygon that we have here. By simply identifying the edges of this square with an orientation, that encodes all of the topological properties of the torus in a much easier to deal with situation. It's easy to talk about properties of this square, whereas trying to visualize and think about loops and curves on this complicated curved surface is much more difficult. So analysis of the topological space can all happen in this fundamental region, and then we can translate those results into the more complicated space using this kind of, well, I explicitly constructed the homomorphism by drawing it. There'll be some concrete way that you can write down formulas for this, but the essential idea will remain the same. Any topological property of this space will be equivalent to topological properties on this space. So using this idea of identifying edges of a square is actually going to get us very far. This was a kind of fairly simple example of a surface we can construct. We're going to see some more exotic examples in future videos, like the Klein bottle or the Mobius strip, which we'll see we can construct using this square, but rather than identifying these edges with their opposite points, we start identifying edges with their kind of diagonally opposite points. And we'll see what kind of interesting properties this gives us in future videos.